Welcome to part 3 of the energy emission and absorption for the Bohr model of the atom. In this video, we're going to be putting more details and more numbers to the process of figuring out how much energy a photon has that's released from the atom when an electron falls back down to its ground state. Conversely, we can also figure out how much energy is needed to get an electron into an excited state or a non-natural state. So over here on the left, I have the line diagram again that we looked at before in a much more basic form, and here you can see a little bit more detail. Now remember that these energy levels, these quantum levels here, represent a state that the electron or the atom is in for at a particular time. Now, what that means is that we have to think of the electron being in a location, but more so in a certain energy state or configuration. And so I'm going to give an analogy here to help us kind of develop an understanding right before we do the calculation. Let's say that in some futuristic country, there's only 3 different amounts of money that you can have. You can either have $1, you can have $6, or you can have $11. That's it. There's no other options. And the money in the country, the actual divisions of money, come in $1 bills, $5 bills, and $10 bills. That's it. There are no coins, there are no other bills. So in order to be in state A, or money level A, you can only have a $1 bill. There's no other combination of things that you can have. To be in state B, you can only have a $1 and a $5 bill. That's it, nothing else. And to be in state C, you can have a $10 bill and a $5 bill. Now you can see another option here would be to have 6 $1 bills to be in this state. And over here, I could have maybe 11 $1 bills. I could maybe also have 2 $5 bills and a $1 bill. And so you can see that there are different configurations that you can have, but they come in discrete amounts. You can never have in between a certain amount of money. And you can't have, say, $4 or $5, okay? That's against the law, and the only things that you're allowed to have are in your possession is either $1, $6, or $11. Now the denomination can come in any form, but that's it. So if I gave somebody a $10 bill here, they'd be able to jump up from being an A citizen to a C citizen. However, if I gave them a second dollar bill, they couldn't jump to either level, and they wouldn't be getting closer to being at the B level. They just couldn't accept that money because there is no official standing to be at that level, a $2 level. Now I know that sounds very strange, but if we think about this analogy in terms of the electron, what we're looking at here are quantum discrete amounts of energy, here money. So in other words, for a particular atom, in this case hydrogen, the atom can only have certain amounts of energy based on the positions that it can be at. It's completely improbable for the electron to be at a $4 level because there isn't really a natural state that relates to that. So in other words, the electron's not making a choice. It's just based on the amount of energy and the configuration that it could be at based on its speed and the position it is from the proton and the nucleus. And so, although this is a little bit of an oversimplified example, what you want to think about is the fact that the electron can only move to an excited state if it gets the exact amount needed to jump to that state. Now, if a C citizen in this money example wanted to go back to being an A citizen, what they could do is they could give up the money in certain installments. Okay, so maybe here in this case I could give a $5 bill, another $5 bill, and then a $1 bill, but I would have to give it up in the amounts that are allowed. So there is no other dollar or coin amount that allows me to break down my contribution back to becoming an A level. Now what that means is, if we go to the atom over here, is that for a hydrogen atom particularly, these are the different energy states. This would be like state A, state B, state C. These are the states that the electron can be in. And at each state, it's associated with a very specific amount of energy. And we're going to show how we get these values here in a minute. Now, the amount of energy that it has at this particular state, it has a couple options. So let's pick an example here. Let's say that the electron is in energy state 3. Okay, so you can think of this as a person who's in the class C citizens. They have $11. Here, there's a certain amount of energy associated with this particular level, but more importantly, what we want to think about is that if this electron naturally falls back down to the n equals 1 level over here, what's going to happen is that it's going to have to give up some energy. Okay, so when it falls back down to the most favorable state, we're going to be releasing a photon, and the energy amount of the photon is going to be the product HF or HC over lambda. Okay, both using some form of Planck's equation. Now, there's different ways you can get down to n equals 1. You can go from n equals 3 to n equals 2, and then from 2 to 1, or you could go straight from 3 all the way down to 1. And in either case, what's going to happen is I might emit some energy here in this transition, and then the rest of the energy over here in that transition. But I can't stop halfway between, because there isn't any other denomination that I can give up. So if I look at the fact that, let's say you're going from C down to A, I can't give up, maybe $2 and then $1. I have to give up in the amounts of bills that I have available to me. So I can only give up in certain cases. Now here in my money example, there are more options than there are in this example. And as the atom becomes more and more complex, it can give up more and more different options, and that's why we saw the line spectra of iron as a lot more than the line spectrum here of hydrogen. Now, don't get too tied up with the names here. It's not as important to have memorized the names, but really all that it's referring to are the physicists that these transitions are named for based on who were the first to observe and to actually quantify it. And so we talk about this Lyman series as being any transition from a higher state back down to state 1. The Balmer series would be any transition where you're starting somewhere else and you're ending on a second level, n equals 2, and then the Paschen 3 and bracket and so on. There's more of them. Now, the energy that's emitted in the terms of the photon here, if you're falling back down to this n equals 1 level, you're actually going to emit a photon that maybe isn't visible to the naked eye. So it might be in the form of a UV ray, okay, so ultraviolet ray. But if you're falling between n equals 3 and 2, you might be able to actually see it visually, and this would be then in the visible spectrum of the electromagnetic spectrum. So in fact, the n equals 1 level was only discovered after, or only measured after, some of the other ones, because of the ability to detect UV rays was a lot more complex than just being able to see them visibly. So let's actually figure out, how do you calculate the amount of energy of the photon? And it's really not that bad, actually, just some adding. So let's take a look at that. So the first thing that we need to know is that if we take the ground state energy and we multiply it by 1 over the quantum number squared, and I'm not showing how we derive this equation here, but if we use this, we can find the energy at any particular level. Now sometimes this is written just as negative E over n squared. Okay, just to simplify it. So what I can do is, let's calculate and see if we can get this negative 3.4 electron volts at the n equals 2 level. So I'll go ahead and put in the ground state amount, which is negative 13.6 electron volts, and then divide by 2 squared. divide by 4, and what I do end up getting is negative 3.40 electron volts. Now, if we want to calculate the energy transition between two different segments, what we're going to do is calculate the energy at the top segment and then the energy at the second segment, and we're going to actually subtract those from one another. So essentially what we can say is that the energy of the photon that is being emitted is the difference in the energy at one particular level minus the energy at the other level. So it's the difference in the amount of energies between the two levels. Now some books will notate N and M, N being the level that you're starting at and M being the level that you're going to, but you don't necessarily need to do that. A lot of times they'll show it also this way, just to signify that N has to be a greater value than M, so you have to be, if you're doing an emission, this is. So if you're going from a higher level to a lower level, that's the only time an emission can actually occur. So what we're going to do here is just calculate them separately. So let's see if I'm going from N equals 2 to an N equals 1 level, I'm going to make the calculation. So I figured out how much energy I have at N equals 2, and that's negative 3.40 electron volts. And I know at N equals 1, I have this negative 13.6 electron volts. So what I'm going to do here is make a subtraction or find the difference between the two. So let's go ahead and do that. So I'm going to say negative 13.6 minus negative 3.4, and I will get 10.2 or negative 10.2 electron volts. But the amount of energy that is being emitted is 10.2 electron volts. From that point, I can then calculate the wavelength or the frequency of that emitted photon. So I'm going to go ahead and do that here. Okay, and I'm going to use the equation E equals HF and plug these values in. So I have 10.2 electron volts for the energy. I'm going to use the form of Planck's constant that is in electron volt seconds. So that's going to be 4.14 times 10 to the negative 15th times F. And so when I do the division here, what I get 2.46 times 10 to the 15th. So the frequency is going to give me around 2.46 times 10 to the 15th hertz. So I can then figure out excuse me, what the wavelength is, and that I can do just by using this speed of light relationship. Now, from this point, I can then decide by looking at the electromagnetic spectrum whether this is something that's visible or if it's UV related, and I can tell what color the wavelength would have to be. We can also go the other way. If I knew the color or the frequency of the photon that was emitted, I could start more with that side. So maybe what I'd want to do is take a look at measuring F, because that's fairly easy to do. So let's say that F, well, let's do it in terms of wavelength, just to make sure we practice both kinds. If I say that the wavelength is, let's say, around 500 nanometers, I could then back calculate, because that's a constant and this is a constant, I can back calculate the amount of energy and figure out what is the excited state that the electron is possibly moving between. In addition, if I do any combination jumps from, say, n equals 3 to 2 and then 2 to 1, then I would need to figure out the energy emitted in each of those transitions, as well as the energy from n equals 3 to n equals 1, because all of those are possibilities, and I might see some electrons in the substance or in the gas falling between 2, some falling straight to 1, and so I would need to figure out that I might get more lines on my spectrum than just 1 or 2 of these combinations. So hopefully that helps in getting you started in understanding some of the visible spectra emissions that we see for, particularly in this case, a hydrogen atom. Now, as you add more electrons, it becomes a lot more complex because if you think about it, there's so many more possibilities for where the electron could be at any given time and what energy state the electron can be in at any given time, and that becomes more and more complex. So hopefully this helps, and in the next videos we're going to start to take a look at a little bit of how energy can be released from a different standpoint, which is in the nucleus itself.